All right, welcome back. Hopefully a couple more examples will help you to just really cement this in your mind and sort of just continually analyzing all different kind of situations and different concentrations and all different ways that this can go, because really it's a grab bag of a whole bunch of different ways it can go. So first and foremost, you just got to know what you've got. And so here we have a strong acid, nitric acid. We have 1 liter of a 0.2 molar, so we know that that's going to give us exactly 0.2 moles of the hydrogen ion. And we have 2 liters of the 0.1 molar NaCN. So we know that NaCN is going to break up into sodium, which is going to do nothing, and the cyanide ion, which could and does, because it's a negative anion that is not one of the neutral ones, it will grab a water molecule and take one of the hydrogens, creating HCN, and that's not negative, creating HCN and hydroxide, but then this is a acid, right? And so what's going to happen is that these H's are going to go, and so every single available CN is going to take one of these available H's. And so what do we end up having here? So we find out that we end up with, if we have 2 liters of 0.1 molar NaCN, we have the exact same amount of moles of CN as we have H. So this is kind of different. So we're going to go ahead and draw this out, right? So here's the net ionic equation. The hydrogen from here, and let's go ahead and pick a different color. The hydrogen from here and the CN from here are going to combine to make HCN, which is a weak acid. Okay, so now when we look at what we've got putting in here, we've put in exactly 0.2 molar of the H's and 0.2 molars of the CN, which will create exactly 0.2 moles of HCN. So 0.2 moles of this, 0.2 moles of that, put them together, what do you have? 0.2 moles there. And so what is our total molarity now in our solution? Because what we've done is we've created a greater volume. So we know we have 0.2 moles of HCN, and we know it's over 3 liters. So we know we have, after we've done this solution mix-up, we have exactly 0.067 molar HCN solution. So we have a weak acid solution. Well, how do you figure out the pH of a weak acid? pH of a weak acid? Let's see. We've got to remember back to all those things we did in acid-base equilibria before. So how do we figure that out? Well, we have an initial amount, and we have these things called Ka's. So pH of a weak acid, remember the Ka, we can solve for the hydrogen ion concentration because it's one of these X's. And we know the initial concentration is 0.067. So we also can figure out the Ka by looking it up in the back of the book. So the Ka for hydrocyanic acid is 4.9 times 10 to the negative 10th. So that is going to equal x squared divided by 0.067. So we'll multiply by 0.067 and then take the square root of both sides, and we end up with this right here. So we end up with 5.7 times 10 to the negative 6, and that equals x, which equals the hydronium ion concentration. So this is all stuff that was in the previous learning. So what happened different here? Well, remember, the whole point is for us to look at, when we put these together, which one ends up in excess, which one doesn't, or if they have an equal amount of each, what are we ended up with? What do we have left over? And once you know those answers, then you just figure out then the pH based off what those remaining things that are left in solution are going to create. So the negative log times our hydrogen ion concentration equals 5.24. And that makes sense. It's slightly acidic. and it's a weak acid, and so not a problem at all with that one. Let's go ahead and do one more problem on this set. What if I had 2.5 liters of 0.2 molar acetic acid, and then I put in 1 liter of potassium acetate? Well, let's look at this. So we know what this is. This, I always forget to do that. This is a weak acid, right? And this right here is just a salt. But what's so special about this salt is it happens to have the ion that is shared with the acid. So we're going to have the common ion effect. And so when you put some extra ion into the solution with the common ion effect, it drives the reaction back towards the other way and creates a buffer. And so we're going to have a buffer situation. So how do we proceed in this one? Well, let's go ahead and write out kind of our scenario. Well, we have acetic acid right here, and acetic acid, of course, when it combines with water, it creates this hydronium ion, and it creates this acetate ion, right? So the acetate ion is a weak base. So this is a base, and this is an acid, right? And we also have an initial input of amount. We have an initial 0.2, so this is our, remember from our ICE table, our initial for this equals 0.2, and our initial for this equals 0.3, right? And so we understand that in the case of a buffer situation, you have an initial input of both the base, the conjugate base, and the acid. And so we learned a nifty little equation for calculating pH, and this is what it was. It was that the pH equals the pKa times, the pH equals the pKa plus the log of the concentration of the base divided by the concentration of the acid. So what will we have to do? Well, we're going to have to figure out what that is. So then our next step is to take this and to figure out how many moles do we have here, and how many moles do we have over here, and can we set this up to solve for pH? Well, it's pretty easy. So to figure out the moles of this, I have 0.2 molar of this, so 0.2 molar of this and 2.5 liters is going to give me a total of, oops, I did it again. I guess I'm Britney Spears. So the crap. Okay, concentrate, focus. Here we go. The amount of the acetic acid put in right here is 2.5 liters times 0.2, and so that's going to give us a total of 0.50 moles. And then over here we have 0.30 moles of the acetate ion, right? And so let's go ahead and just plug in our numbers. So what about pKa? Remember, pKa is the negative log of the Ka. So if I look up the Ka of my acid, which is acetic acid, it's 1.8 times 10 to the negative fifth. So my pKa equals negative log of that, which is 4.74. So my pH is going to equal 4.74 plus the log times the amount of the base divided by the amount of the acid, and I get 4.52, which makes sense. One of the reasons this does make sense is that it's close to the pKa. The pH of a buffer is always very close to the pKa of the acid that's in the buffer situation. So the pKa is a really good tool to sort of gauge whether or not we have correctly figured out the pH of this. So notice 4.52 as compared to 4.74, very close. And so because they are so close, we realize that this is probably the correct answer. And so that solves that, and hopefully that gives you a heads up on how to do some more of these solution situations.